Daniel Perez, a PhD student in data shape and the Laboratoire de Mathématiques d'Orsay, will give us a lecture on barcodes of random functions on the circle. Let's go.
Okay, so thank you, Pierre, for introducing me. So as Pierre said, I'm going to present what the barcode of a random function looks like. Sorry. So some motivations is, for a long time, people have been trying to study what the barcode of a random process on some manifold looks like. So there are some partial answers to this, in particular in expectation. And there have been some results for some particular processes, such as for Brownian motion, for example. But we would like to have something stronger. In particular, it would be nice to have some almost sure results on the barcodes of random functions. So this in general is not necessarily a trivial task, but for the simple case of one-dimensional functions, we can say quite a bit of things. In particular, if the processes are Markov, then it is possible to give a nice description of the barcodes of these processes. So for the rest of this talk, we will focus on Markov processes, and in particular on Brownian motion. So we will illustrate the general principles that apply to Markov processes with the particular example of Brownian motion. Okay, so let's start by reviewing a little bit what is known in the literature. So one of the main results, which is due to Frédéric Chazal, who is present here, I think, and Vincent Divol, is that essentially we know what happens on rectangles of the persistence diagram of Brownian motion. And so we have a formula for the distribution of these variables, which I called nxy here, which is essentially counting the number of points in the diagram that lie within the rectangle, which is here. So we have the law of this, and it depends on this function psi, which will come back later. So please remember it if you can. It's not very important, but it would be nice. And essentially, so there's this very, it seems like a very complicated integral to study, but nonetheless, at least we have a closed expression for what the law of this nxy looks like. So number of bars between two certain levels, x and y, will actually tend to infinity as you let x and y just tend to each other. And so if you study the divergence of this, then it turns out that the divergence goes like something like x minus y to the minus 1. And in fact, if we rescale this by the divergence, then nxy actually tends to the local time of Brownian motion. And so in particular, we have that for all h and r, we have the following expression for the expectance, for the expected value of this nh minus epsilon, h plus epsilon, which is the following, where here this phi hs is nothing other than the density of the random variable distributed like a normal random variable with mean 0 and variance s. So it's clear from the formula before that making any kind of estimates for the formula with the big integral is painstaking and a little bit long. So this is the first observation. It's a little bit too much to be working with this formula all the time. And the second statement is that we would like to say something more. So because right now what we know is essentially what the barcode looks like in a rectangle of the persistence diagram, but we don't know that much about what happens overall in the whole diagram. So one of the solutions to this is instead we could study the number of bars which have length more than epsilon, say. And this random variable we will call n epsilon from now on. And for the rest of this talk, we shall actually study the properties of this n epsilon. So the first step is maybe to start simulating what happens to this n epsilon. And so essentially, so here's a simulation. And so a couple of remarks about the simulation. The first remark is that essentially the way I did it is I just computed lots of paths, of Brownian paths, and then I calculated the persistence diagram for each one of those. And so essentially the curve that is here is the expectation of an epsilon. And so here we see how it depends on epsilon. And these, so this part of the diagram here, essentially don't pay too much attention of it. It's just a numerical error. So this stair thing is not, I mean, it's just due to the way that I did the simulation. So that's an important remark to make. But nonetheless, we see in this diagram that there are two distinct regimes. Namely, when epsilon tends to 0, we seem to have like this like power law essentially, and when epsilon tends to infinity, then we have a different regime here. And so essentially, we will study what happens in both of these regimes. So what is going to be the general strategy? Well, we need a way to count the number of bars which we have. So if we have some one-dimensional function, then typically the bars correspond to essentially the connected component. So you want to count the number of peaks in a way. And so how are we going to do that? Well, of course, to have a peak, you need to go up by a certain amount, but you also need to come down and then go up again a little bit. And so essentially, we are going to define these points, which we will call TIA or TI epsilon and SIA or SI epsilon. And essentially, these are depicted here. So the logic is if you reach some peak and you come down a distance A, the point where you have come down a distance A from the peak is called TI epsilon. And similarly, if you reach a minimum and then you go up by A or epsilon, then this time where this occurs is called SI epsilon. And then you keep going on like this. So again, you reach some other peak and then you come down by A and then you have some other TI epsilon. So now the problem is, okay, we have this idea, but we want to write a formal expression from for these TI epsilons and SI epsilons. So the way that we are going to do this is essentially the following. So if we have some continuous function now, then we can define these SI epsilons and TI epsilons in the following way. So we're going to do it by recurrence. So first, we start by setting S0 epsilon and T0 epsilon as 0. And then we do some recurrence like this. So this looks complicated, but essentially the logic is you want to reach a peak and then you want to come down by epsilon, and you look at the smallest time such that you have this happening. And similarly for the S epsilon, the logic is that you want to reach some infimum and then you want to come back up by epsilon. So essentially this gives you this expression, and you want to do this in the minimum time possible. So because of the definition of this as an infimum of times, these actually turn out to be well suited to be studied probabilistically. And in fact, it turns out that these TI epsilons and SI epsilons are actually stopping times. And so it follows that since we're studying Markov processes, this is nice because essentially they're all independent from each other. And so we can calculate, provided that we can calculate the densities of these stopping times, then in principle we have access to the law of the process that we're trying to study, as we only need to count the number of these TIs and SIs. So this is essentially what I try to convey by the following formula here, which is essentially saying that, so the number n epsilon that we were looking at earlier is nothing other than the infimum of I, such that TI or SI is equal to infimum of the empty set, where what I mean by this is essentially you're taking the infimum of, so the set inside the infimum here has to be empty. And so this can happen. So you look at the smallest I such that this happens, and based on this, then you can find the number of n epsilon. All right, so this is the general strategy. So now if we actually do the computation, we can actually calculate this as follows. So if now we have x, a continuous stochastic process on 0, 1, and if we suppose that x satisfies the strong Markov property, then we can write an analogous formula to what Chazal and Divol found in their paper, except now it's a little bit more complicated because we have these densities of these stopping times, which are depicted here. And I chose this notation because, well, it's easier to write the integral in this way. But essentially, you have a very similar formula. It's just the densities change. And so this formula here is valid for all k is strictly greater than 1. And for the particular case of k equals 1, then of course this p, the probability of having an epsilon is greater than or equal to 1 is nothing other than the probability that the range, which from now on I will call R, so that is the supremum minus the infimum of this process over the whole interval, is greater than epsilon. That's just saying that essentially the minimum minus the maximum has to be equal to at least epsilon if we want to have a bar of at least length epsilon. So this is essentially what this is saying. And so if this is the case, then we have the theorem in a complete manner for all k. And so once again, the expression is quite similar to what was found in the paper by Chazal and Divol. The only thing that changes is the densities. So if we look now at the particular case of Brownian motion, it turns out that we can actually calculate the densities of these stopping times. And so essentially you get the expression that you had before, except Brownian motion is special because it is not only a Markov process, it is also Lévy. So that means that these stopping times are all identically distributed, which actually greatly simplifies your task because you only need to compute the densities of these stopping times once. And so because of this, you can find you can actually find this density for Brownian motion, and it's given by this horrible formula here, where psi is the same function that appeared in the Chazal-Divol formula. So this formula is nice for a couple of reasons. The first reason is because well, heuristically, it's kind of inclusion-exclusion formula based on the formula of Chazal and Divol, except, of course, you're doing this an infinite amount of times because you want to have everything above a certain diagonal. And so essentially, you can sort of see it like this. So this is kind of why you have this psi appearing again. But then, of course, in practice, it doesn't really work that way. So this is not actually how we find this formula. But it's nice to see that there is at least some kind of consistency with respect to this. And so, like I said before, we have a similar expression for all Markov processes. But of course, the exception is going to be that the densities in the integrand are going to be, well, we're not going to know what they are. Okay. So now, okay, again, we have found this complicated formula, and this is all good. But again, studying this is kind of difficult because of the expressions. And now, in fact, if we look at the formula in all its generality, then it's even more difficult to study because we don't even have any sort of control over what these densities actually look like because it depends on the process. So we would like to still find some kind of asymptotic dependence, which makes our job easier in a way. And so to do this, we start by examining what happens in the regime where epsilon tends to infinity. Then if you can imagine that if epsilon tends to infinity, so epsilon is very big, then the number of bars in the barcode is essentially either 0 or 1. So either you have the range being greater than epsilon or it's not. And if this is the case, then you're done. So this is basically what happens for epsilon very, very large. And so it follows that it should be the case that when we have very large epsilon, that the expected value of this n epsilon should be very similar to the probability of having this range greater than or equal to epsilon, essentially. So this is the first remark. And the second remark is that if k is greater than 1, and now we care about the probability of this n epsilon being greater than k, then in some sense, what we should find is that this is like achieving achieving a range of epsilon 2k minus 2 times. And the reason for this is because, well, we have to go up by epsilon once, and so that gives us a first peak. But then if we want 2 bars, then we need to come down and then go up again by epsilon. So this is why you have this 2k minus 2 factor here. And so essentially, like what you have to do is kind of jump up and down by epsilon at least 2k minus 2 times. And the probability of doing this is essentially the range being greater than epsilon. And so it should sort of depend on something like this. And in fact, it turns out that this intuition is correct, and you can prove it. And so in particular, we have a theorem that says that indeed the expected value of an epsilon is asymptotic to the range. So the probability that the range is greater than or equal to epsilon as epsilon tends to infinity. And furthermore, you can actually also bound the density of the process in the following way. So again, the probability of an epsilon being greater than k is actually less than or equal to the probability of the range being greater than epsilon, again, because you sort of have to jump up and down 2k minus 2 times. And since the process is Markov, then all of this is, quote, independent. And so in a way, this is why you have this product happening. And again, so once you have a bound on the distribution, then of course you can give a bound on the expected value simply by summing everything here. And so if you do this sum, then you get the following expression, and that will give you a bound on the expected value of an epsilon. So this, in fact, is valid for all Markov processes. So for all Markov processes, we have we know asymptotically what the expected value of an epsilon will look like, and similarly we have the bounds, provided that we know the density of this random variable r, which I recall is the range of the process. And so so this is actually quite nice. So one can wonder, okay, but this is nice, but does it actually work? So we check for the particular case of Brownian motion. And in this case, we actually know what the range looks like. So the distribution of the range for the Brownian motion, and this is a theorem by Feller, is that it's something like this horrible formula. And if you do the asymptotics of this sum, you will actually find that this is asymptotic to this quantity right here as epsilon goes to infinity. And so if you plot this quantity, then you actually have a curve like this. And as you can see, for large epsilon, it's quite clear that this fits quite well. And in fact, what is a little bit shocking is that you don't actually need to have epsilon that large for this formula to start working really well. So as you can see, if we have a value of 1, this starts working very well already. So this is the first asymptotic regime. So now we want to attack the problem of studying what happens when epsilon goes to 0. The problem is, of course, that the tools of persistent homology are not necessarily well suited to study the small bars because, well, multiple reasons, but among others, everything in that has been developed kind of neglects what happens at the level of small bars. So we need to think of a different way of approaching the problem. And well, digging a little bit in the probability literature, you will see that trees are objects which come up very often. And so one is tempted to think that in a way there should be a link between the trees that the people in probability study and persistent homology. And in fact, it turns out that there is. So first I will detail a little bit how you can actually build a tree from a function. And then after we have built this, then we can look at how it's related to persistent homology. So the way that you do this formally is you give yourself a pseudo distance on 0, 1 defined in terms of the function. So the explicit expression in 0, 1 is given here. So essentially you take the points and you have this expression, which we will come to back later why this works. But one of the remarks that I will make is that this this pseudo distance actually has the nice property that it correctly identifies the connected components of the super level sets of F. So this will be important because we are talking about from now on we will focus on talking about the super level sets. So whenever I will refer to the persistent homology, I will always mean the persistent homology of the super level sets, as opposed to the conventional quantity in TDA, which is to look at the sublevel sets. Of course, for Brownian motion and any symmetric process, this makes absolutely no difference, because in distribution, whether you take minus the Brownian motion or the Brownian motion makes absolutely no difference. Nonetheless, in general, it is a distinction that we should make. Okay, so this is the first remark. And the second remark is, so in fact, it turns out that because this is a pseudo distance, you can quotient 0, 1 by essentially all the points where which are a distance 0 away from each other. And if you do this, it turns out that what you get is an R tree. So essentially, it's a tree. So how does this work exactly? Okay, so for the moment, just focus on the blue curve, which is essentially our function, and the tree, which is drawn here in red. So I said before that this pseudo distance correctly identifies the super level sets. And so the reason for this is the following. So if we place ourselves in between 2 points here, so you see these 2 points, they are a distance 0 away from each other, because essentially the minimum in the expression of the pseudo distance is achieved at exactly these points. So essentially what you have is that the distance is f of x plus f of x, because they have the same value, minus 2 times f of x. So essentially it's 0. So you can see that this is correct. And so if you can have fun, and you can actually study what happens over all of the points, and it turns out that this indeed collapses essentially the level sets, which belong to the same connected component of the super level sets. So in this way, you get some tree like this. And so the tree, which is constructed by this function, is given here in red. So this is how you construct this tree. So right away, the fact that this correctly identifies essentially the connected components is essentially why this is connected to persistence homology. And in fact, the relation is given exactly under the form of an algorithm. So the algorithm goes as follows. Essentially, you have some tree. So you start off with the tree of the function that you have constructed. And this tree is rooted, and it has a root because if provided that you start over some connected manifold, then of course you have that for a value which is low enough, you'll have the entire manifold. So essentially, at some point, this tree will have a root. So you start with some rooted tree, and then the logic is, okay, so we take the longest branch starting from the root of this tree. So we look at, okay, what's the longest possible branch? And in this case, it's the one I draw here in red. And then we are going to assign to this longest branch, and it's the first one that we have done. So we assign the infinite bar, essentially. So we assign this, and once we have done this, we delete this branch of the tree. So the next step is essentially, okay, we have deleted this branch, and we have a forest left. So now, in particular, it is a rooted forest. And so we play the same game, and we say, okay, starting from the roots of this forest, where is the longest branch in this forest? So in this case, the longest branch turns out to be this one. And so this will give you the second bar, which you can identify by basically looking at the height of this branch. So you just kind of assign this branch to this bar, and then you delete the branch in question. And then you keep going on like this. So the next one is, for example, this one. And so this one will give you this bar, and then you delete it, and you keep going on like this until essentially you have nothing in the forest left. So in this way, you can construct the barcode from the tree. And okay, in fact, now you can say, okay, this is nice, but what happens if we have an infinite tree? And there's a little bit of a complication, but in general, like this, one can see that it should work. And so, in fact, this tree actually encodes more information than the barcode when we see the barcode simply as a collection of Betty numbers at every single point. The reason for this is the tree actually carries information about the generators of the homology. And so this extra information is actually quite useful, and so this is what makes the theory a little bit richer. So so now, okay, I'm going to define what I will call an epsilon trimming of the tree, which essentially is kind of giving the tree a little haircut. So the logic goes as follows. So we can define this h tau function, which, okay, you can read the definition, but essentially it's easier to see it in a picture. So given some branch, some point in the tree, tau, then we can assign a function h tau, which essentially looks at the following. So you take this point tau, and you look at all the points which are above tau, and in particular, you look at the length of the longest branch above tau, and so this gives you some function which is called h tau. And so h tau here in the example that of this picture, if you pick tau here, then of course the longest branch is this one, and so h tau is given by the height of this branch here. And so in this way, then you can define what I call a haircut of the tree, which is essentially you cut all the branches which have length less than tau, less than epsilon. So what does this look like when you give the haircut of the tree? Then, okay, now you have this picture again, except now we have the tree here in dashed. And you see now what we have done is for every branch of the tree, we have essentially cut all the branches which have by a length a in this picture. So you see this is essentially how this works. So you just cut all the branches which have length less than a. Or another way to say it is that you take the points in the tree such that h tau is greater than epsilon. And so if you do this, this is basically just cutting down the tree a little bit. And so in particular, once we have done this construction, then in fact, it turns out that this n epsilon, which we were trying to study from the start, is nothing other but the number of leaves of the tree that got a haircut, tf epsilon. Okay, and in fact, this also corresponds to the concept of an epsilon simplification presented in some of the TDA literature. Because you see, once you have constructed this, then there's a quite natural function which you can look at, which essentially consists of the function where you cut off all the peaks and you just extend by the constant function. And so if you do this, you get an epsilon simplification because you have reduced all the bars which have length less than epsilon. All right, so why are these trees important and what do we gain by studying them? So one of the main theorems is that in fact, the metric properties of these trees are actually related to the regularity of the function f. And so in particular, if f is a continuous function, and now I'm talking about any continuous function, it's not necessarily a stochastic process, on any 1D manifold, then we have the following equalities. So we have this quantity VF, which is equal to this lim sup, and is equal to the upper box dimension of the tree. And this VF is what quantifies in some sense the regularity of the function f. So what it is exactly is the infimum such that the p-variation of the function is finite. And so in particular, we will note that if the function is alpha Hölder, then this quantity VF is actually less than 1 over alpha. And so you can see that this theorem, is linking metric properties of the tree with the regularity of this function. And in fact, these two quantities are also related to the growth of this function n epsilon. And so in fact, if you study the small bars, you get access to information about the process, quite important. Okay, B trees, so in particular for Brownian motion, for example, we can actually say quite a bit of things, which are a little bit richer than the previous theorem. So if X is a Lévy process now on 0, 1, and we suppose that almost surely X has no interval on which it is monotone, which actually happens quite often. So for example, Brownian motion has this property. Then there exists some function psi epsilon, which we have an expression for, such that this psi epsilon actually tends to 0 with epsilon. And if you take this product here, in probability, it will tend to 1. And so if we know something about the growth of this psi epsilon, then in fact we can say that the convergence here is actually almost sure. So this is actually quite a powerful statement. And one of the remarks is that one can compute at least the epsilon dependence of this psi epsilon quite easily, provided that the process is self-similar. So in particular for Brownian motion, this is the case. And so computing the epsilon dependence for Brownian motion is actually quite simple. So let's look at what this theorem says for the Brownian motion. And what it says is that all you will have is asymptotic. Okay, so this 1/2 you need to calculate, but essentially the power law is given by the self-similarity. And as you can see, the exponent here is 2. And the reason for this is because the Brownian motion, well, one of the reasons is that Brownian motion is 1/2 minus delta Hölder for all delta greater than 0. And so, okay, now we can wonder, okay, but this is nice, you have this dependence, does it fit? So it turns out that it does. So again, don't worry too much about what's going on with this staircase. But as you can see, it actually fits quite nicely as you get to epsilon very small. Okay, so of course, now that we have done this for Brownian motion, you can ask yourself whether we can do the same for other processes. So for example, one of the most natural things to look at next, Brownian bridge. So this is now a function which is on this, where you can see the Brownian bridge as a function on the circle. And so it's quite interesting to look at what happens for this case. It turns out that it's a little bit harder to study the Brownian bridge because it is not a Lévy process anymore. And so there's a little bit less that we can say. But nonetheless, the theorem that I presented linking regularity and the up box dimension of the tree still tells us that essentially the following asymptotic relation should hold almost surely. That is, that for all delta greater than 0, we should have that essentially the growth of this n epsilon should depend something like should be less than epsilon to the -2 minus delta as epsilon tends to 0. But in fact, we're tempted to say more because, okay, fine, you know that this is true, but you also know that Brownian motion is nothing other than a conditioning. The Brownian bridge is nothing than a conditioning of the Brownian motion. So you're still kind of tempted to say that the paths should have essentially the same behavior at a very, very small scale. And so a conjecture is that, in fact, this n epsilon should be exactly the same as for Brownian motion. But the problem is that there are no theorems which easily allow you to just say, okay, this is clearly true. But you intuitively you would like to think that it is true. And so I conjectured that this is actually true, but unfortunately I could not prove it. And so what about the large bars then? Well, for the large bars, we have that the expected value of this n epsilon should be asymptotic to the range being greater than epsilon. And again, because these ranges are actually well studied by people that work in probability theory, we know it is a rather classical result that this range is given by the following expression. And so we know quite well also the asymptotic dependence of this expected value. And so again, you can ask, does it work? And so I did a simulation for the Brownian bridge, and this is what you observe. So for large epsilon, it actually works quite well, as you can see. And for small epsilon, well, you can kind of see that it kind of works, but after a while, because the simulation is finite, it fits, but as a more refined simulation is needed before we're able to say anything conclusive. Okay, so this is for the Brownian bridge. So now some concluding remarks. So the first thing is that in theory, we have an expression which allows us to compute the law or the distribution of an epsilon for all Markov processes. But actually calculating this distribution can prove very difficult because there's this very difficult integral that you need to actually compute. And this is actually most of the time impossible in practice. It depends on the process, but if you cannot find the densities, it's basically you're hoping for too much. But nonetheless, you can find some asymptotic things, which is quite nice. And so the second point is that all the results given are applicable to Lévy processes. And Lévy processes are actually kind of even nicer than Markov, because in this case, the calculation of the stopping times might be actually achievable. So this is the first thing. And the second thing is that we actually have finer results as far as the small bars are concerned. So this is the second thing. And so the third point is that all the asymptotic results I gave are actually valid for Markov processes, except the result of the finer asymptotics for the small bars. So the study of these trees in probability theory has shown a couple of things. So the first thing is that we should be looking at persistence diagrams themselves as metric objects. So we know that the collection of persistence diagrams is a metric object, but we should be looking at a persistence diagram also as a metric object, because it is also a tree, as we have seen. And in this way, we can study some new invariants, which actually stem from the metric on the persistence diagrams themselves, such as the Hausdorff dimension of this object, or the Upbox dimension, or other metric invariants, which you can define. And these turn out to be significant, in particular when we are looking at processes which are very irregular. And the reason for this is because they, as we have seen, turn out to be related to the regularity of the processes which you're studying. So this is one of the remarks. And finally, the small bars actually play a very important role in the study of stochastic processes. So they cannot and should not be discarded, but rather be studied carefully, as there is some very powerful information which is encoded in these very small bars, and in particular in the growth of the number of the small bars. And that's it. That's it for me. So are there any questions?